The intensity of a star is 1,650 watts per square meter from a distance of 1.4 times 10 to the 11th meters. What is the power output of the star? What is the temperature of the star's surface if it has a radius? I am sorry, this cannot be determined. Okay, sounds like we got two questions going on here, right? So let's figure out the power output of the star, right? So the intensity that we've got is going to be the power output of the star over the area over which it has been spread, right? Which will be the power output of the star over 4 pi r squared, where this is the radius of that imaginary sphere over which that power has been spread. Remember, intensity is watts per square meter, right? Okay, so that means we're looking for the power output of the star. So that's just going to be, power is going to be the intensity that we've got times 4 pi r squared. We can do this. So it's going to be 1650 watts per square meter spread out over a pretty big area. 4 pi, and then this is our radius, 1.4. Okay, notice that's watts per square meter times square meters, so that'll be just watts. Watts that unit? Times pi times 1.4 E11 squared. And this is 4.0639 times 10 to the 26th watts. So it's brighter than the sun a little bit, right? The sun was like 3.85 times 10 to the 26th. This guy's brighter. Because we're also a little bit closer to it, right? But that's, yeah, I don't know. All right, so then that's what's the temperature. We'll use we now know the power output of the sun, right? So we'll use the Stefan Boltzmann E sigma area temperature to the fourth, and they're just asking us for this temperature, right? Notice how they never, when they talk about stars, they never we never worry about the incoming radiation from the universe, and that's because the universe's temperature is extremely cold. It's like 2.736 kelvins or something like that. So we don't worry about the incoming radiation. If you're a hot object out in deep space, you're the only show in town. There's no incoming radiation of any significance. I'm sure there's neighborhoods where that's not true, but not for this star. I'm telling you that. Okay, so let's see. We're solving for temperature. So that's going to be, temperature is just going to be power divided by the emissivity, sigma, the area, and then that's going to be raised to the 1/4 power. So let's do that. Let's see, it's 4.0639 divided by, and then it's like, what do we use for the emissivity? Just use 1. Well, we assume that they're perfect radiators. Maybe it's for lack of imagination. I don't know. Okay, and then our area is going to be quite large for this star, for 4 pi. And then this is just the area of the surface of the star, right? What's interesting is with stars, the size of the star dictates its temperature, its brightness. Because the bigger the star, the more the gravity is, the faster it feeds fuel into the fusion furnace that's driving it. Okay, so the number in my calculator, I'm going to go left parenthesis, that number divided by left parenthesis 1 times 5.67 e minus 8. Don't forget to multiply by 1. Okay, times 4 times pi. This is all in parentheses, so I put this entire denominator in its own uber set of parentheses, okay? 5 pi times 9.3 times 10 to the 8th. I'm going to square that. Okay, right parenthesis, I'm closing out my denominator. Another right parenthesis, and I'm going to raise it to the 0.25. Let's see if this thing just crashes. Ooh, I got it. I got it. The temperature is 5067.5. It's like at some point you open and close enough parentheses that you keep track of them. Apparently I did. There we go. Which is 5070, right, with that. A lot of watts, a lot of kelvins. So evidently that star is not quite as hot as the sun, but we're closer to it. It's bigger than the sun. I don't know. Something's messed up. I just made the numbers up, so I don't even know that a star with that radius would have this temperature. Probably wouldn't. All right.